So here are some energy problems, and they're actually really simple as long as I don't make a mistake. So the second floor of a house is this high above the street level. How much work is required to lift this big of a refrigerator? By the way, 293 kilograms is 600 pounds. I don't know about refrigerators. Maybe they are heavy, but maybe not that much. Anyway, so it asks for how much work, and then I put in there, you can also compute potential energy, because all that work will be turned to potential energy. Whatever the means are, pulley system or what have you, if you just straight lift it up, it would be force times height or force times distance. And so I'm going to plug in these numbers. As I said, they're really easy as long as I don't make a mistake, and I do make a mistake right now, and we'll catch it in a little while. So 293 times 5.9, and using the calculator would be 293 times 5.9, which rounds to 1,700 to sig fig, but it's the wrong result anyway, because the mass is given in the problem, but work says force times distance. Well, what's the force here? Well, the force that tries to pull the refrigerator down is, of course, its weight, and its weight is not 293 kilograms, it's 2,930 newtons rounded, multiplied by 9.8 or 10. So that's what I need to do, and that's what's missing here. I'm going to put that one in there, and I'm going to do times 9.8. So this calculation here, hold on, clear second entry, there we go, times 9.8, doesn't matter in which order I multiply. 16,941 rounds to 17,000 because it's two significant figures. As I said, alternatively, that is the correct result now. Alternatively, I could calculate the potential energy, which is mass times gravity times height. Well, turns out that, of course, it's the exact same thing as this one here, which means I don't have to do that again. It's 17,000 joules. 9.8 is always a positive number. Unless the equation tells you that there's a negative, you consider it to be a positive number. And that makes sense too here, that 17,000 joules, that's how much you gain, so to say, in putting that amount of potential energy into it. All right, give myself a little break here for the next problem. Okay, again, relatively simple problems, just plugging in numbers. So railroad diesel engine with this much mass and that much speed, compute its kinetic energy. So kinetic energy is 1/2 mass velocity squared, so 0.5 times 44,000 times 5.5. 5.5 meters per second is roughly 12 miles an hour. I double it and then round it a little bit up. So it's not very fast, but notice because of the 44,000, it's going to be quite a huge amount of kinetic energy. So let's see, 0.5. And then typical thing is to forget the square. There is a square, so don't forget it. Enter. 665,500, 2 sig fig, 670,000. There we go. Did I get it? Yeah, I think so. Okay, next problem, really similar to this one, but now the diesel engine has coupled with a freight car. Oh, I should put the freight car a little bit closer there. There we go. That's a little bit better. And then they move off together, and because they coupled, the diesel engine has slowed down due to the impact, and the freight car, of course, has accelerated, and then they coupled together, and so they're moving off together. Mass is, let's see, mass is given here, the total mass of the two, so 51,000 kilograms, and then the speed is 3.2. Notice that that is appreciably smaller. Yeah, calculate. So, oh, same one, same equation. I just hit second entry and go back and fix my numbers. There we go. I could have just typed that, actually. It would have been just as fast. Enter 260,000 joules rounded. Notice that is 410,000 joules less than before. Well, that happens during the impact, that some of that kinetic energy, actually an appreciable amount, has been converted to heat and noise during the impact. And that's what I say right here. This one is an inelastic collision. Some initial kinetic energy is converted to heat and noise in the coupling. So what was it again? 260,000. What's the answer? There we go. All right, and this problem here. This question is typical on some driver's license exams. Turns out I really haven't found it on a driver's license exam. However, I did find it on some insurance documents where they're talking about that. So a car is moving at this speed. I know that's just a little bit off the screen. There we go. So moving at this slow speed, skids for 54 feet with lock brakes. How far will the car skid with lock brakes at this much faster speed? The way to do that is just to compute the ratio, 82 over 32, and then multiply by the original braking distance, and then you get the answer, except that's wrong. And here's why. This one here I got from the text. I'm going to try to scroll down. So this is actually from the conceptual physics test. Besides that, interestingly, the maximum friction that the road can supply to a skidding tire is nearly the same whether the car moves slowly or quickly. That is not the case for air resistance. Air resistance does increase at higher speeds, but apparently friction between the tires and the road is just about the same as at high speed as it is at high speeds as it is at low speeds. Now, here comes the thing. So the first one was just an interesting statement, but here comes the thing that's relevant to this problem. A car moving at twice the speed of another car takes four times as much work to stop. Okay, so what's happening here? Why 4 times? Well, here's what's happening. The kinetic energy is this, 1/2 mass velocity squared. All that kinetic energy needs to be transformed to something else because you're going to get rid of it in the braking process. You're going to stop, so you're going to have zero kinetic energy. So all of that is being transformed and therefore equals to the work that's being transformed due to the friction on the road. Oops, I tried to highlight the friction. There we go. Times the braking distance. And since all the kinetic energy transforms to work and therefore equals the amount of work that is given off, this one results. And notice that I highlighted the distance and the velocity squared. So if you double the velocity, you get twice the braking distance. If you triple the velocity, you get 9 times the braking distance. So that's what that means, and that's what's on these insurance sheets. And therefore, this is the way I wrote it here. I said this is a ratio problem, so I have to apply this work energy theorem twice to get this one here. So here, instead of just having the ratio of the two speeds times the distance, it's the squares of the velocities, the ratio of the squares of the velocities times the distance. And I already prepared this here because the equation editor is quite cumbersome in this software. So I'm just going to pull my calculator. There we go. And it's going to be 82 squared divided by 32 squared. Turns out I don't have to pay too much attention to denominator and numerator, but I will do it anyway. So times 54, which means I have to go all the way to the front, which takes a long time clicking. There we go, and I insert an opening parentheses. So 82 squared divided by 32 squared times the original 54, which comes out to a whopping 350 feet, 2 sig fig. And so, no, it's not just a little bit more than double the 54. It's quite a bit longer. 350 feet is more than a football field. Of course, you're already going at 82 miles an hour. By the way, notice that I didn't use American units. Yes, we can do physics with American units. Usually it's harder though. All right, so these were a few of the energy problems. So in a moment here, I will cover these conservational momentum problems. And then after I was done recording, I figured, oh, because I'm talking about the momentum before and the momentum after, I should have supplied two drawings. So I forgot the second drawing here, so here it is. For the Superman problem, before anything happens, they're both addressed. So Superman is just leaning onto the asteroid, and then he pushes the asteroid off to the left, and that means he gets a push back, and that's this drawing here. And there we go. I think we can see it. So he pushes the asteroid to the left because the asteroid has much more mass than Superman does. That's why its velocity is relatively small, and Superman's velocity is relatively large. Okay, the other problem that I did then is this one here. Again, it's the before and after. So the diesel engine runs into the freight car, has a certain velocity, and then as it runs into it, the two coupled together have a smaller velocity, and that's what we can see here in the after. And then for this problem here with the shark and the fish, so before the shark is going to the right, the fish is swimming to the left. The shark eats the fish. You can see him here in the stomach. And due to the impact, the shark has slowed down. That's why the velocity is smaller after lunch due to the impact. And again, these drawings that you just saw, these second drawings, that's what I forgot in the upcoming recordings here. So just picture them. Here they are. All right, so here are a few problems on the conservation of momentum, which is the same as the Newton's third law. So equal and opposite forces just expressed in different ways. So in this problem here about Superman and the asteroid, I highlighted the information as given. So Superman's mass, the velocity of the asteroid, that the asteroid is this much more massive than Superman is. I highlighted those in yellow. In whatever violet color that is, I highlighted what it's being asked for. And in blue, I highlighted that both the asteroid and Superman are initially at rest. That is implied information. And that means, of course, initially at rest, that both of them have zero velocity and therefore zero momentum. All right. Before I actually get to the conservation of momentum, here's a shortcut that I want to share. And notice that the shortcut is very quick. That's why it's called a shortcut. I'm simply going to take the ratio of their masses, 863, and I multiply with the velocity of the asteroid, ignoring the negative. And when I do that, I come up with, get rid of this here, 863 times 54, enter 46,602, and to round it to 2 sig fig would be 47,000 meters per second. So that would be Superman's velocity as he pushes the asteroid to the left. He gets the same force back because his mass is much, much less. He ought to come up with a much larger acceleration and therefore much larger velocity, 47,000 meters per second. That's roughly 100,000 miles per hour. You don't see that in the comic books because they don't want to make it look strange, but that would be the correct physics. And again, he's Superman. Okay, keep this in mind. This was just a shortcut. By the way, here's also the reasoning why the shortcut works, as the mass would otherwise divide out. And we can almost see that in a moment when I actually do the conservation of momentum. By the way, the asteroid that I chose here is called Ida, number 243, which basically means it was the 243rd asteroid that was discovered possibly in the 19th century. I would have to look that up. And then much, much later, when the spacecraft Galileo went by in the 1990s, it was discovered that it actually does have a little moon, which is called Dactyl. Despite its very low gravity, small mass, low gravity, it actually is able to hold on to an asteroid moon. All right, so conservation of momentum. means that the momentum P before is the same as the momentum after. And I pretty much write this one here for any kind of these momentum problems, the collision problems, or this is the reverse of a collision, so that we have the momentum of the first object plus the momentum of the second object is the same before as it is after. So that's left to right, before and after. Okay, so before anything is happening, well, both are addressed, so 0 plus 0, which obviously is 0. That means also that what happens afterwards, that's still 0 combined. Notice that there will be a negative here. The asteroid goes to the left, so whatever momentum the asteroid has, Superman makes up for it by having a positive momentum to the right, and hence the two will actually equal out to 0. Okay, so here is the mass of the asteroid, which is given as 863 times 79. And if I really want to, I can use this little times there instead of the x. There we go. And I do need more space, I think. So here's this velocity of the asteroid, negative 54, which by the way is about 100 miles an hour. And then plus the mass of Jupiter, mass of Superman, 79, times his unknown velocity. So that means I have to multiply all of this, get it to the other side, and then divide by 79. So I'm going to get the calculator. Trying to find it. There it is. Let's see. So 863 times 79 times 54. I know it says negative 54, but I'm going to put it to the other side, so I add it on both sides. Hence, it's a positive number, which makes sense because Superman's velocity needs to come out to be positive. Then I divide by the mass of Superman, 79. Notice at this point, actually, the 79s would be actually dividing out, right? Which is why I exactly come up with the same result as earlier with the shortcut, and which is why the shortcut actually worked. But it only works because of the way the problem is worded, because it says this times it's this much more massive. In any case, I get the same 47,000 meters per second rounded for Superman to sig fig because of the numbers that are given. All right, take a little break here. All right, this problem here with the diesel engine and the freight car. Notice this is also kind of strangely worded. So here is the diesel engine running into the freight car. The freight car is at rest. I put that again in blue. And the information that is given then here in yellow, this time is more massive. The mass of the freight car itself is 11,000 kilograms, which means that 3.2 times more massive. The diesel engine is in the neighborhood of like 35,000 kilograms. The diesel engine originally has a speed of 4.5 meters per second. Bumping into it, now again, Newton's third law is the same thing as the conservation of energy. So when I just talk about forces, even though I'm not computing or using them, but when I talk about forces, then the diesel engine is exerting a force on the freight car, which accelerates that one, but at the same time it gets the same force back, so that decelerates the diesel engine. So the diesel engine is going to be slower. So from 4.5, well, that's only 9 miles per hour, by the way, or 10 miles per hour. So it's going to be slower, maybe around 2 or 3 or something, respectively, since it's relatively heavy compared to this freight car. I'm guessing it's going to be in the neighborhood of like 3 to 4 meters per second. Then the two couple together, which means they go off with the same speed. Okay, here's the shortcut. Shortcut a little bit more complicated than the Superman problem. So here I take the ratio plus 1, so this is a 4.2. This one here is the ratio itself, 3.2. And then this one is the initial velocity, 4.5. And then I made a mistake. Yay. Because that actually gives me a number that is larger. So this is the way it's supposed to read. Oopsie. So I have to fix something here. There we go. That's the way it is. All right. Fix my shortcut. 3.2 divided by 4.2 times 4.5. And that's kind of what I predict between 3 and 4, 2 sig fig, so 3.4 meters per second. Again, the reason why this shortcut works is because of the way the problem is worded with this. This is much more mass, and then actually the mass would divide itself out. But let's do it the proper way. So I'm going to move this out of the way. I need some more space here, I think. Conservation of momentum. So the momentum is before, the momentum before is the same as the momentum after. So again, this here would be the diesel engine and plus the freight car. And then after that, the two are coupled together. That's why they both have the same final velocity. And I simply add the masses between the two. So on the next line here, I'm going to plug in these numbers here in just a moment. This would be for the diesel engine. And this one here is the freight car, which is initially addressed, hence plus 0. So, okay, so here I'm going to type in the numbers. That one is 3.2 times 11,000. That would be the mass of the diesel engine times the initial velocity of 4.5. There we go. And I do need more space. Whoops. Pull that a little back though. And then here, I would have the two coupled together, and I guess I could calculate that out. 3.2 times 11,000 for the diesel engine, 35,200, so right there, 35,200. By the way, I could also write that over here. I will. 35,200 plus the 11,000 from freight car. Okay, and now what I have to do is on the left-hand side, multiply this one here at the 0, doesn't matter, and then divide by the sum of the two masses on the left-hand side. So let's see, 35,200 times 4.5, divide by, I can do that in my head, 46,200, which then gives me the same answer as before, around at 3.4 meters per second. Right there. And the reason why, again, the shortcut worked from earlier is because all the masses here include 11,000, so that kind of divides out, but there's one 11,000 more. That's where you get the plus 1. And that's also where I initially messed up my shortcut earlier. Put it in the wrong way. All right. I'm going to give myself a little break here and then go to the next problem. So, shark and fish. So shark, that's a real 7-kilogram shark. That's a really small shark, actually. It's only about 15 pounds. Swimming to the right at the speed here, 5 meters per second, swallows an absent-minded 1.1 kilogram fish, which compared to the shark is actually pretty big. You know, that's a huge lunge. 2.5 pounds or so compared to the 15-pound shark. Swimming to it at a speed of negative 18 meters per second. So the fish itself is actually pretty fast. I highlighted the numbers that are given. I also highlighted what it's being asked for, which is the velocity after the shark ate its lunch. Again, because of the impact here between the shark and the fish is being slowed down, going to the left, and then the shark is also being slowed down due to the impact going to the right, which means that the velocity of the shark ought to be somewhat less than the 5 meters per second that are listed there. And it's kind of hard to predict if the shark is just going to be slowed down, or if he comes to a stop, or if he actually being reversed. If the fish would be a whole lot faster, the shark could actually be going backwards. I doubt that's what's going to happen. In any case, I just talked about Newton's third law with the forces, but it's the same as conservation of momentum. So the equal and opposite forces is the same as applying it to the momentum before equals momentum after. So on the left-hand side here, that would be the shark plus the fish. On the right-hand side, well, again, the two masses are added because the shark ate the fish times the final velocity, which is what we're looking for. Okay, so mass of the shark, 7 kilograms. Notice the 1 sig fig. Our answer, therefore, will be also 1 sig fig. So times 5. I guess I could have let's see if I can fix that right here. There we go. That should read shark, and that should read fish. If I could do that earlier. And is it still highlighted okay? Yeah, kind of. There we go. That's good. All right, so 7 plus 7 times 5 for the shark, and then for the fish it's 1.1 times negative 18. And then after the shark has eaten the fish, it's the shark's mass, 7 plus 1.1. So I have to multiply this out here and add, and then I have to divide by the total mass. And as I said, I ought to come up with something that's less than 5, but I don't know if it's going to be 0, if it's going to be a little larger, if it's going to be a little smaller. So I'm just going to do that. Let's see, again, push that a little over here so I can see the calculator better. There we go. 7, I'm going to put this in parentheses on the left-hand side. 7 times 5 plus 1.1 times negative 18. So that's the momentum on the left-hand side, which I divide by the total mass from the right, which is, again, I can do it in my head, 8.1 kilograms. Enter, and I come up with 1.87, but because it is 1 sig fig, I ought to round it to 2 meters per second. So that's how fast the lunge with the swallowed fish is after lunch. Shark.